Hello there, thank you for joining me again today. On the bench we've got a radio frequency power meter manufactured originally by Marconi Instruments. Then it became IFR when IFR took over Marconi, and then subsequently after that became Aeroflex, which took over the brand afterwards. These meters have been around a very long time. They've been around since the late 1970s, early 80s and onwards, and these are very widely used across all the radio frequency engineering sectors, from aerospace to defence, radar applications for example. CW measurements, pulse measurements and CW measurements can be undertaken by these, and they also have an extremely wide operational remit, from measuring small signal power amplifiers or signal generators right the way up to high power RF and pulsed applications as well as CW. Now the nice thing about these is that I've seen these throughout many years being used in various things, from aeronautical radar to marine radar and weather radar systems, and really handy pieces of kit for that, simply because the very wide frequency range that the instrument can work at, and that's down to these sensors. Now these sensors are actually shared with other Marconi instruments, such as the microwave radio test sets, which I've done videos on, because they unplug from the front of the unit, and we basically got sensors that can go right up to about 46 gigahertz, and also with varied power level handling as well. Now you've got to be careful with these, because a lot of people assume because it's an RF power meter, they're often sold without the sensors, and then people assume that these N-type sockets on the front are actually where you connect your RF signal in, and not realising that they can cause damage, because this is not an RF input, this is an output, which I'll go into in a moment. So be wary of that if you see these advertised and you're thinking of buying one, because often the sensors themselves cost far more than the instrument. These microwave power sensors are different to the SCALAR sensors, which I've seen used on the microwave test sets that I have, which I feature in the other videos that I do. The SCALAR sensors and the power sensors have got unique differences, which I'll show you. But basically the SCALAR sensor, the lead itself, the actual wire, goes directly into the SCALAR sensor on the Marconi range of sensors. However, on the RF power sensors like these, the sensor unscrews. There's a connector here, and so the connector unplugs from the back of the sensor, and that's the difference between them. To look at them, they're almost the same, apart from the SCALAR sensor is actually a bit slimmer, only a touch though, whereas the RF power sensors are more fatter. Now this particular sensor goes up to about 4.2 gigahertz. The other ones that I've got, which you've seen in the other videos, go up to about 46 gigahertz, 20 gigahertz, 26 gigahertz and 46 gigahertz. And generally these only measure power in the milliwatt range. There are some sensors that you can get where they have heatsink fins here on the collar of this N-type plug, and they can measure up to a couple of watts CW, but generally speaking they don't measure high power RF. Now the meter itself is designed to measure from a very low RF level of just microwatts right the way up to kilowatts if you use the right sensors with it, but most of the Marconi range of sensors only go up to milliwatts or a few watts here or there, not really high powered levels. So how you achieve the high power measurement capability on this is you use external attenuators such as this one. Now this goes up to a 4 gigahertz, which is adequate for this sensor, because obviously that goes up to 4.2 gigahertz as well. So you would use a level of attenuation to reduce the signal down to a safe level. Now on these sensors they are actually marked up quite clearly what levels they can take. Now if I just move that, you can see there on this sensor what levels it's designed to work at. Now if I just try and zoom in, so we've got minus 30 dBm, which is 1 microwatt, to I think it says plus 20 dBm, which is 100 milliwatts, in a frequency range of 30 kilohertz to 4.2 gigahertz. So the other sensors give data as to how much RF power they could take in a pulsed application as well, which can be hundreds of times higher for a pulsed signal as opposed to a CW signal. Likewise as well, there's a chart on the other side which gives information about the linearity, calibration factor, duty cycle, etc. on the different frequencies throughout its frequency range is written on this table, and that's quite important data, because what we can do, we enter that in here. There's a button for linearity, which in my case is 7.08, which I've entered in, and then Cal Factor, and various parameters that we can put in there. Now on the instrument itself, we need to calibrate that sensor before we can begin using it. So this is where this port is here, this N-type, which is not an input. Quite a lot of people who are inexperienced inadvertently and accidentally connect RF in there and blow the unit up. This is an output, not an input, and so we can set a signal up to come out of here, which the sensor uses then to calibrate itself. It's a 1 milliwatt or 0 dBm level at 50 megahertz, and that's what it uses. We've got auto cal features, auto 0 here, which we're going to use in a moment. So before we get into doing any calibration or whatever, we've got the power switch here. There's also an analog meter as well, which comes in handy. We've got auto ranging. We can change the units of measure as well, limits, and we can store memories, etc. We've got average and range, so we can go between different sensitivities. Recall memory locations as well. Obviously we can enter in all the duty factors and linearity data, and then we can do the calibration modes and auto zeroing. So it's quite basic, but yet quite featured in the same sense. So we'll connect the microwave sensor up to the the power sensor up to the front of the instrument on the calibration port. Now obviously these are not just meant for microwave radio frequencies, with the sensor having a range of 30 kilohertz to 4.2 gigahertz in this case. We can actually use it in HF and VHF and UHF applications as well. So I'm just having a little bit of difficulty just trying to get it to bite onto that N-type socket, and which is always difficult when you're working one-handed with a camera, and they are a bit of a pain. The tolerances on the N-type plugs and sockets that are on the Marconi range of instruments are quite tight, so you've got to be really spot on when you mate up the connectors, otherwise they'll not mate up. So we've got it back on now. Right, so we've got here just down in this section we've got a auto 0 and auto cal. So we'll go for the auto cal. What that will do, it will put the reference on and then calibrate this against it. So that's what we'll do now. And it's just starting the calibration sequence. And then basically when we put the source on, it should read 0. So it's calibrated the internal reference against the power sensor being calibrated against the internal reference. So now we're ready to begin measurements, because what it's done, it's stored that info into the memory of the machine. Now as for units of measure, at the moment it's reading dBm, but you can change that to milliwatts, watts, microwatts. You can do what you want with it. And round the back of the instrument we've got this is the same enclosure, by the way, as what the Marconi frequency counters use, which you'll have seen on my other videos as well. But basically round the back we have a number of plugs and connectors on the rear, which I'll go into in a moment regarding what they do when we look at the technical description as well. The voltage input selector switch as well, and the IEC lead as usual, that kind of thing. So let's just jack it up so we can see it. So on the rear we've got the recording, so the data, the analog levels that are coming out of the instrument on the measurement can be recorded there. We've also got a level adjust via this blanked off plug here, and a DC input option as well. And again, some of these things are blanked off. On some of the meters there's a socket here, so you can have a sensor plugged in on the rear as well as on the front. Then you've basically got on the back here, you've got your 3 BNCs, which are for the recording output, 2 fuses, 2 30V and international voltage select, an IEC, and then you basically got the GPIBs fitted. It'll be behind this blanking plate, and that gives you the information there about it. So very nice little instrument, as I say, been around for many years. Very capable little RF power meter, but you've got to be so careful with these to make sure that you don't damage them, because as I say, they are very sensitive, the sensors, and by applying too much RF onto these burns them out quite easily. Likewise DC bias as well. You know, when you're looking at amplifiers, small signal amplifiers that are mast fed up the centre of a coax, microwave radio links for example, that again fed with a 48V DC bias, it can burn them out quite easily, because it's not designed to take a DC bias unless otherwise noted on the labelling. So these sensors themselves are often more expensive than the instrument on its own, because of all the tech, if you like, the measurement capabilities all in the sensor, not in the instrument. So that's why often when you see these for sale without the sensors, people buy them thinking, oh, you know, there's an RF N-type socket on the front there, we can just connect in RF power as well. Now Marconi did make a handheld version of this that did have an N-type socket on the top, and it's more like the size of a portable multimeter, and that can take RF power directly as well. They did do one. I've never had one myself. I've seen plenty of them, but I've never actually seen them in use, to be honest. But I have seen them advertised for sale and on popular auction sites, but never owned one myself. I think they're battery operated as well, those handheld ones. But anyway, that's the nice thing about these sensors, is that you can share them between different Marconi instruments. So you know, they're great for that. Now if you buy one of these and upon turning it on, you just get the 2 message. That's because it's not seeing a sensor here. It's got to see a sensor, otherwise it'll come up with an error message. So that's something to be aware of if you're buying one. It's not that it's got a fault with it. You know, if you haven't got the sensor, it's natural that it comes up with error 2. And I've got some sticky stuff on my fingers there. I don't know where that's come from, but I think it's come off this socket. Some kind of lubricant or grease that they put on to stop moisture from getting in the connector. Now there are on the odd occasion you can drop on lucky if you buy sensors for these that are cheap, where the cable itself's got a break in it, and often you know, you can get lucky that way. I have done repairs on these sensors under microscope, and I'll do a video on what's inside these, because there's power handling and measurement circuitry is built into the N-type socket here in that neck, and the 2 gold wires that come out which connect into the circuit board, and all the intelligence is basically in there. And you know, they are very delicate, so you've got to be so careful not to damage those. Otherwise, you know, you can lead yourself into a very expensive situation. Generally speaking, when you're buying these second-hand, these sensors, be careful, because quite a lot of them are damaged already. They've had excessive RF power fed up them. This only measures microwatts and milliwatt levels, and you will get people that connect them to back of high-powered radios and transmit into them at 20 watts, and then burn them out and then sell them. So you know, it's so precarious when you're buying these, unless you've seen it calibrated like that on a cal, you are taking a chance. Okay, so one of the examples that we can use this in is for testing the output levels on a signal generator, and also as well, not only that, you can use them in radar applications, or pulsed radar via a directional coupler or a sniffer, or attenuator if you're measuring direct power from a power amplifier stage. So you know, it's always better if you are using these with an high power RF source. Start off with the largest attenuation first. It's always better to have too much attenuation than too little, because obviously, you know, you could damage the sensor quite easily. So start off with a big attenuation, and no point in using an attenuator as well that doesn't work well at the frequency that you intend to use it at. This particular RF attenuator goes up to 4.5 gigahertz, which aligns with what this sensor can measure, but I wouldn't use that with a 20 gigahertz signal, because obviously if I'm using a 20 gigahertz sensor, you'd want an attenuator that can handle up to 20 gigahertz as well. So this is where calibration can go out the window a little bit if you're starting to use attenuators that are cheap, that are not precise attenuation factors, or indeed that they are not capable of attenuating at the frequencies you're using them at. So you've got to be very careful with that and make sure you use the right attenuators with the right sensors. So what I've done, I've set up an experiment just as an example of what we can use this with. We've got a signal generator set up, and what I'm going to do is I'm going to demonstrate it by connecting it to this signal generator here under RX test. Get it on the right screen, and then I can select a frequency, whatever it is, RF gen level, and then I can basically RF gen level, and then say 0 dBm, or if it won't go to it, we'll go to, in this particular case, we'll go to minus 20 dBm, and then we'll see just how accurate the output is of the signal generator. We've calibrated the sensor on the on here to 0 dBm, and all we need to do is just physically connect it up onto the N-type connector on the RF signal generator, and then make sure it's nice and snug, not over tightened, but just tight enough. And then we've got the measurement coming up now. So this is averaging and settling, and you can change the ranges as well. We've got the little meter as well just here, which is measuring. So it says minus 20 dBm, which correlates to what we were measuring, or what we were sending out on the radio test set on the signal generator. Now as I reduce that level by turning the knob down to say, let's say neg 40 dBm, then obviously it'll start to go down to its lower limit. Now its dynamic range on that sensor, I think when we looked at it earlier, I think it was neg 30 dBm or something like that. So you wouldn't expect it to measure beyond neg 30. So you've got to know the capability of the sensor that you're using, otherwise you'll you'll not be measuring properly. And as you can see, it's starting to get down there now, around about neg 30, and then I don't think it'll be able to measure much beyond that. You can set up different averaging as well on here as well. Average, there's range as well, so you can go between different ranges, which I think is range 2. So if I increase that level back up to around about neg, and put minus 7 dBm in, right, 02, So we've got it on auto, enter, and then range 5, enter. And you've got different ranges, you see, that you can use. So, and it'll tell you on the screen there under range, and then you can reduce the range again. So we can do range, and then we can do say 5, enter, or range 4, range 1. Or auto. And then as you adjust the RF level on the test instrument and whatever, you can see there that the starting to -40, we're at -69 at the moment on the test set, but it's out of its range. It's only when you get within its dynamic range of the sensor. There we are, look. That's -20 dBm. Auto. And then range. Let's try different ranges. There we are. So we've got the correct ranging now. It's within the bar graph on the meter there, and we're reading -19.7 dBm. So you can go between different ranges, make it more sensitive if you like, or more deaf, depending on what you want to do, and then you can adjust its range. So that signal generator is, you know, spot on. It's -20 dBm, and yet and that's the application that you'd use it in as well, because you're measuring the signal directly at the source, whereas if you're using RF cables, like with a spectrum analyzer for example, you'd have an RF cable connecting from the SIGGEN up to the spectrum analyzer, then you would simply introduce more losses, because obviously the cable has loss. So this is a method of measuring a signal directly without having any losses to cater for in cables. So that's a particular usefulness of this instrument, plus as well, you know, the microwave test set uses that as a benefit. So these are quite useful for doing calibration work, for measuring pulse signals, CW signals, etc., in conjunction with the 30 dB attenuator. You would need to enter in the data on for very precise measurements, like I've done here, the linearity, duty cycle and Cal Factor data that's written on the side of the sensor. Otherwise it won't read accurately. It'll still read accurately with the calibration here, but for super accuracy, as per the calibration house that calibrated the sensor, then you enter the data in here, and then the finer calibration detail is held within its EEPROM then. Now on the other range of test sets, microwave test sets such as these here, they remember the sensor that's connected in. There's a little EEPROM in the sensor that talks to this, and you can get it to remember the calibration data for different sensors, so you're not entering in all the table each time you're using it. So that's quite an advantage as well. So they're quite clever in that sense. But yes, they'll last many years. The only thing I don't like about some of these instruments, like the frequency counter and these, they don't have a backlit LCD display, which would be nice. Really nice if it did have that, because in high light environments where there's a lot of light in the workshop, you get glare off the screen, plus as well the display can be difficult to see in very bright sunlight conditions as well. So that's the only thing I've got against it, really. So yeah, the technical blurb on these, written by Aeroflex, which I'm gonna discuss now. It says that it's a precision power meter with comprehensive GPIB facilities for ATE, automated test equipment requirements and standard bench applications. Anyway, it says it's got an extensive frequency range of 30 kHz to 46 GHz. It's got a wide dynamic range, depending on what sensor you use with it, from -70 dBm, which is equivalent to 100 picowatts, to plus 44 dBms, which is 25 watts. So again, you'll be able to get sensors that have a heat sink, the fins like the RF attenuator does there on the N-type. So the attenuator is built into the sensor, so you can get them that can measure up to 25 watts RF. Or alternatively, you know, with the 25 watt sensor, you can even use over attenuators as well before it, so that then you can measure even higher powers, up to kilowatts if you wish. It's got a fast response on the GPIB of 25 milliseconds, auto averaging with manual override. They offer sensors in both 50 ohm and 75 ohm impedances. There's a low sensor VSWR which reduces measurement uncertainty. It's got a sensor linearity correction for improved accuracy, a maximum hold facility, an optional DC operation if you want to run it from batteries, and a non-volatile memory. It says the 690B RF power meter is a high accuracy instrument which, together with its associated power sensors, provides measurements at frequencies from 30 kHz to 46 GHz of a wide range of power levels. Its numeric keyboard enables easy manual control, while full GPIB implementation with SRQ, mask and trigger modes make it the logical choice for fast ATE systems. So again, that's where these will be used in mainly laboratory environments, or for example production environments, etc. Now for the meter accuracy, the 6960B features an instrumentation accuracy or better than 0.5% in linear mode and 0.02 dB in logarithmic mode. It says a special auto zero circuit digitally stores the zero offset for each of the 5 ranges, thus reducing zero carryover errors to plus or minus 0.03% and providing a zero accuracy of plus or minus 1% of FSD on the most sensitive range for any sensor type. Now it goes on to say that it's obviously got the high accuracy because it says that the power sensors are provided with detailed calibration data to 0.01% resolution. In addition to calibration factor data, each sensor is individually calibrated for linearity. When entered into the power meter, the data reduces linearity errors to less than 0.5% plus or minus, even at the highest range. The precision calibration attenuators, it says the 6920 series of high sensitive power sensors are supplied with a precision 30 dB attenuator for calibrating to the internal power reference. These attenuators have an accuracy of plus or minus 0.05 dB at 50 MHz to provide high calibration accuracy. Duty cycle correction. Although the 6960B is a true average power measuring instrument, it may still be used for pulsed power measurements. The duty cycle of the signal to be measured may be entered into the range 100 to 0.001%. The power meter calculates the peak power by dividing the measured average power by the duty cycle. So for relative measurements, the dB relative key, which I think is, where is it now? I'm sure I've seen relative, there we are. The dB relative key, it says enables the measurement of high powers by entering the calibrated value of an attenuator or coupler directly as a negative number. So this is where we talk about this attenuator. So at the moment it's set to 0 dB because we've got it connected on the straight to the source. But if I was to attach this 30 dB attenuator in, we change that level there to 30 dB, and we'd obviously enter that there 30 and press enter, and then it would take that power level into appreciation. So that's where that is quite useful in this application. It says positive relative values to account for amplifier gains can also be entered. The dB offset linearity facility may be used with linear units so that the transmitter output powers can be displayed in watts. So that's how you turn this micro watt meter capability into watts. So by using external attenuators to the sensor. So there's two power-up modes. The instrument is provided with two power-up modes for production line testing or applications in power monitoring at unattended sites. Power-up mode 2 returns the instrument to its previous settings after switch off or on power failure, and power-up mode 1 sets the instrument functions to default values. So basically it can be used, you know, in a remote application at a hilltop radio site for monitoring of RF signals, and then obviously used to trigger a report if the level falls below a certain level. So it's got two proportional voltage outputs, which is what I believe is on the rear panel, those BNCs we were looking at earlier. It says here, it says two analog voltage outputs proportional to the RF input power are provided on the rear panel. It says the recorder output offers a full 50 dB dynamic range of the instrument in the dB mode at 1 volt stroke decade for wide range power measurements. In the watts mode, this output provides 0 to 5 volt linear voltage proportional to the RF input power. The fast leveling output provides 1 volt per range for effective power leveling of sweepers or signal sources. It says the calibration and linearity correction data from the sensor are traded off for fast response. For semi-automated testing, the rear panel blanking output is provided to turn off a source or sweep generator during auto zero operation of the meter. So in other words, we can get this to follow a sweep generator, so it'll follow that and then measure the RF curve, if you like, or trace of a given source. So ease of use with its environmental, with its conventional calculator style keyboard, changing parameters is both precise and obvious to the new user. Displayed units may be either linear milliwatts or logarithmic dBm. Applications which require circuit adjustments to optimize output or tune for null are conveniently achieved with the analog meter, which is obviously this on the left. It says automatic signals averaging is provided as well as auto ranging. The power meter selects the most appropriate amount of averaging in conjunction with the range in use. So regarding noise, it says for applications needing a fast response on sensitive range, the user can trade off resolution for speed by entering the low range number. The 6960B accepts average numbers between 1 and 256, so optimum noise reduction or required response time are always available. It's got a non-volatile memory, a maximum hold capability, automatic sensor recognition as well, a GPIB operation. It's got 6 trigger modes on the GPIB, which includes TR trigger mode. This sets up the trigger mode or starts the instrument after a hold condition. Up to 6 trigger modes are available from the 6960B, from free running to fast to intermediate trigger with setting, time, then hold. Now it says here that there's an SRQ response to the system user. The SRQ response is always important, and in the 6960B the SRQs have been arranged to form a mask with each SRQ option having a binary weighting: 1 on end of measurements, 2 on error, 4 on end of GPIB operation. SRQ option 4 is used to inform the controller that the requested GPIB operation, such as auto zero, has been executed. Self-test is initiated when the instrument is switched on, and the validity of information in the non-volatile memory is automatically checked. it says the LCD alphanumerics are annunciators, and annunciators can be verified using the coded key press. Reliability, the 6960 series has a proven record of high reliability. Data from service record shows its actual mean time between failures MTBF to exceed 120,000 hours. Conservative component ratings, liquid crystal display and switch mode power supply for low internal heat generation contribute to this excellent reliability. Consequently, a 2-year warranty is offered as standard, with an optional 3rd-year warranty available at the time of the initial order. So basically it says that for the specification, the frequency range is 30 kHz to 46 GHz depending on the sensor used. The power range is minus 70 dBm to plus 44 dBm depending on the sensor used. The power reference, which is this N-type socket here, gives a 0 dBm 1 milliwatts output at 50 MHz. On the Type N precision connector, 50 ohm. The uncertainty is plus or minus 0.07%, traceable to national standards. The accuracy is plus or minus 1.2%, worst case for 1 year. It's a 4-digit LCD. The instrument accuracy, watts mode is plus or minus 0.5%. In dBm mode, plus or minus 0.02 dBs. And in dB relative mode, it's plus or minus 0.02 dBs again. To 0, it says plus or minus 1% of FSD on most sensitive range. Then it talks about all sorts of things to do with calibration factor, resolution, and the capability and the accessories and things that comes with it. So that's a little rundown on that meter, and at least you've seen it used in a particular application. So you can use it to measure high power RF. You've just got to enter in obviously the dB relative on there in order to you know, putting the external attenuation in. I'll set it back at 0 dBm so it's reading you know, the what will be correct level. 0 0 0, enter. Will it do that? No. Calling me a liar now. So I'll have to figure out how to do that. That's the other thing, there's a second function on these keys as well, so and some way of doing it. You've always to faff about with these instruments, you know, when they've got second functions on these keys. There's a way of being able to get round things, but that's what you have to learn when you use all these different instruments. You know, it's quite interesting when you're jumping from one instrument to another. You know, you're jumping from an instrument like that, and if you get that off a shelf and you're starting to use it and you think, well, how do I do this, and faff about with it until you get, you know, the manual out and start reading it, and until you know how to use it, and then you jump to an instrument like those over there, and then these here, all these instruments. So you've got different user interfaces between the different manufacturers, Marconi, Hewlett-Packard, Aeroflex, Rohde & Schwarz. They're all different with the way that you use the instrument. So it's actually quite a useful instrument to have on the bench. It's quite small, compact. It's nice to be able to pop it on a shelf and put it away in a box somewhere, you know. So it's not a big clumsy machine. It's quite a very compact unit, and of course it's the same size as the Marconi series of frequency counters, so you can stack it on top of other pieces of kit. It's quite lightweight as well, it's not too heavy. And so I'll just move on now to showing the sensors themselves and the different types of sensors. So this is what we were referring to earlier as being the SCALAR sensor, where the wire connects directly in. So they look very similar to the RF power sensors, obviously side by side. You know, there's not much real difference between them in size, just a little bit maybe, but the SCALAR sensor can't be used as an RF power sensor with that meter. If you tried plugging in this sensor, although it's got the same connector on the end of the wire, it won't actually read it on there. It'll say sensor error or unknown sensor type. So that's the difference between a SCALAR sensor, which is used on a SCALAR network analyzer, versus an RF power sensor. So don't be fooled by that, even though that they've got the same plugs at the end to connect into the radio test instruments or power meters, etc. Because a SCALAR sensor won't work with the Marconi, obviously, or the IFR power meter. So that's why you've got to be careful about those. It probably may, on some of them, it might tell you that it's a SCALAR detector as well. Mate with precision connector. It might actually say something on there about it, but I can't see it on there anyway. Whether it says it's a SCALAR detector on it or not, but it probably does. There's probably somewhere on it where it says what it is, but again, it'd be easy to miss if you were purchasing one, you know, if it's not shown on the on there. Marconi instruments, and then it just says Stevenage, England on it. It doesn't actually tell you that it's a SCALAR detector. The only way you'd know it with a SCALAR detector is the type there. That this one is obviously a 6511, and that's the only way you'd know, by typing that in on the internet or whatever, is it coming back and saying that's a Marconi SCALAR detector, because they've all got type numbers on them, you know. Like that, for example, is a 6912, I think it is. So that, yeah, 6912 power sensor type. So that's how you'd know. It's difficult if you're not familiar with them. So, but at least you've seen a SCALAR detector versus an RF power detector, and the differences. Obviously, as I said, the RF power detectors have always got these connectors on the back, so when that's removed, then you've got the plug on the back, whereas the SCALARs obviously don't. So at least you've seen that. So this is just showing the different sensor types. This one here goes up to 46 gigahertz. This has actually got the air dielectric in it, or a K series, I believe it's called, connector. It looks like an SMA, but it isn't, it's a K. This one is a very high frequency rating. That one is basically, I think it's the same, 100 and something, 15 megahertz or something, up to 46 gigahertz, 40 gigahertz. And then it's got a power measurement range there of minus 30 dBm to plus 20 dBm, 100 milliwatts. And then you've got the calibration data there on it. So you've got the calibration factor 100%, frequency and cal factor then for all the different frequencies, right the way down to 40 gigahertz. And the accuracy is 9 there, which again, all this data here would be entered in on the instrument. I managed to find out from the last part of the video as well, where we had the unit of measure in there for external attenuator, and when I had it set to 30 dBs, if you remember, I couldn't get it back to 0 dB, because if I pressed 1, for example, it went back to 1 dB attenuation, but when I pressed 0 and pressed enter, when I went back to dB relative, it hadn't gone back to 0 again. It didn't matter what number you entered, you know, then obviously each time it was 5 dBs attenuation, and I just thought, well, why want it at 0? Well, unbeknown to me at the time, if you just press dB relative and then the decimal point and then press enter, when you press dB relative again, it comes back to 0. And it's knowing little things like that, you see, in the middle of a measurement or when you're in a rush, it can be annoying, that kind of thing. Because you'd think, you know, if you'd entered a 30 dBs, messed it up again, but if you entered a 30 dBs attenuation in, and then obviously that's what you were using, and then you change the attenuator, or removed it and you wanted to put 0 dBm in, you know, you should be able to press 0 and then press enter and it should take it, but it doesn't, you see. That's the nice little thing about Marconi things, they throw these little curveballs at you. But pressing 1 dB attenuation remembers it. So who would have known to press a decimal point, and that would. And what's interesting about it is as well, it will accept 0.1 dB, you know. So again, why, if it can accept 0.1, why can't it accept 0, you know. Again, so the decimal point, press enter, and then it's back to 0 again. And as you can see, it's measuring, you know, the 20 dBms nearly that's coming off the test set that's down there that it's measuring. So it's little things like that. So yeah, we've got these sensors obviously, and you can extend its frequency range and power handling capacity, and they come in these little nice cases and things quite often to protect them. And then we also have a waveguide variants as well, which are these sensors here, and these are very heavy. These are like solid brass, where we've got the different WR waveguide sizes, and made by Marconi Instruments again. So we can measure waveguide, microwave signals with those. So that's what they are. But again, there's all sorts of different sensors, you see, and things you can get. So the biggest problem you've got with these power meters, really, to avoid damage, is if you don't know what level of attenuation you need when you're making an RF measurement, then that's when you're going to risk the most damage. Because if you're measuring a 50-watt transmitter, for example, and you've not chosen the right RF attenuator, if the RF level coming into this sensor exceeds more than 100 milliwatts, then you'll damage the RF sensor. So what I would advise anybody to do if you use an external attenuator is to get a known RF power meter, a proper bird through line meter or something like that, and connect it then to the output of the attenuator before you connect the sensor, and just make sure that, you know, you're reading less than 0.1 of a watt on it, and if that's the case, you know, it'll barely move a needle on a bird through line meter. But if that's the case, then you can obviously know that when you connect the sensor up to the attenuator that it won't damage the sensor. So sometimes you have to just be cautious, just make sure that when you're using such attenuations with these very delicate sensors that you've made sure that the output level from the attenuator doesn't exceed the input level that this can take. Otherwise, you know, this is very expensive. These are many, I don't know what they were brand new, they're probably, you know, £4,000 or £5,000 each. These may be more, but you know, even second hand now, these are very expensive. So this is why you've got to be so careful not to damage them. So, you know, sometimes it's better if you wanted to measure high output levels on something to use a dedicated meter for doing that doesn't use such sensitive. It's not always possible, obviously, at microwave frequencies, because a bird through line RF power meter, for example, can't work at 20 gigahertz. You know, it might be able to work up to 1 gigahertz to push, but it certainly won't be able to measure much more than that. So this is why these meters are so useful. But you've got to make sure that the level of attenuation you use doesn't exceed or allow the excess power to make it through to the sensor, otherwise you'll damage it. So anyway, I hope you've enjoyed this video. By all means, if you like it, please subscribe, add comments in beneath, and we'll come back to you with further videos. And thanks very much for watching. Take care and see you in the next one. Bye.